Okay, so in this example we have a radar antenna which is rotating about a fixed vertical axis at a constant rate of capital omega, and we're told that the angle theta is increasing with a constant rate theta dot. We're told the observer and the little xyz axes are attached to the antenna dish, and the capital xyz axes are fixed in space. Given this information, we're asked to determine the angular velocity of the observer as well as the angular acceleration of the observer for a given value of theta. Okay, so to work this problem out, we'll start by computing the angular velocity. And if I do this, I'm going to note that at this instant, the angular velocity is composed of two components. We'll have first of all the rotation capital omega, and because that's about a fixed axis, I'm going to designate that to be in the capital J direction. And then I'll add to that a second rotation rate, which will be theta dot, and this will be about an axis which is actually rotating in space that I'll designate by little k. Now I'll come back in a few minutes and express that in a consistent vector set, but for now let's move on and compute the angular acceleration. So if I use the product rule of differentiation, I can express this as omega dot in the capital J, plus omega in the capital J dot, plus theta double dot in the little k, plus theta dot in the little k dot. In the problem statement, I'm told that capital omega as well as theta dot are constant, which means that of course the first and third terms go away. If I note that the capital y-axis is a fixed axis of rotation, that means this unit vector capital J dot will go away. And so what I'll be left with here is an angular acceleration that's solely a function of theta dot and little k dot. Keep in mind that the time derivative of a rotating unit vector is simply given by omega crossed with the unit vector itself, which is k. So if I do some substitution here, this is going to give me that the angular acceleration is theta dot times quantity omega, which is omega in the capital J, plus theta dot in the little k, crossed with the little k vector. Now if we stare at this problem for the instant where theta is given by the given angle, we'll note that the axes are not aligned, with one exception, that is the little k and capital K axes are aligned. So in this regard, I can go ahead and figure out the angular velocity by simply substituting the little k for the capital K. Pardon me here, let me sketch that back in. That'll give me a consistent answer all in the same unit vector set, which is always what you want to do. And if I utilize that same fact, I can essentially replace here the little k with a capital K. And of course I could do that here as well. And if I go ahead and then express this, the answer, I'm going to have this is going to be theta dot times omega times quantity capital J cross little k. And so you'll note here k cross k goes to 0, so I'll get the final result, which is that this is simply theta dot times omega in the capital I. Okay, I have both the angular velocity and angular acceleration in consistent vector sets, so we should be good to go here. I'll let you plug in the numbers. Best of luck.